So today we were getting into, as we wrapped up last week, we were kind of getting into the actual practical application, performing ultrasonic testing. And so I was starting to talk about what you're going to do in labs. So here we have, what you would see. You're going to have a screen similar to this one. This isn't our exact tester, but it's a similar setup to our tester. And just a few things to point out. You can see we've got our probe on our test object there on the left. And there are, some of the different parameters we talked about. We have a gain level that we can adjust up here. We have our range, which affects what we see the scale across the bottom. So in this case, this part would be, it's in inches, and it's 0.5, so the total thickness of the part is a ½ an inch thick. Okay. And then some of the other things down here at the bottom, you can see we've got a velocity in inches per microsecond. Okay. And then the 0 point is what shifts this entire graph left to right, and that takes into account the fact that, remember, the piezoelectric crystal in here is not sitting right at the very surface of the probe. It's going to be up inside the probe a little bit, and then there's a wear plate along this bottom surface. So the sound has to travel a certain distance from the piezoelectric crystal inside of here to that front face or that top face of the object. And so that's what this 0 does, is we don't care about that. So we're just going to shove that off the side of the screen. Okay, if we had a 0, if we had no delay here, then this initial pulse, this big peak at the beginning on the left side of the screen, which is the result of the sound entering the object, that would actually be sitting over just a little bit to the right. And it also accounts for the fact that when the sound returns to the transducer, there's going to a certain amount of delay as it gets from the face of the probe up to the piezoelectric crystal inside of it. So those are the different settings we have to do. The last one here is delay, and that is if you were to add what's called a delay line, or basically a piece between the probe and the work piece and the test piece. That would be used if you're trying to find surface type discontinuities and that kind of thing. So as we move this probe along to an area that's flawed, you're going to see an indication that starts to look like this. And I showed this last time, but just kind of a review of that. So you can see if we compare these, our back wall echo, that's at 0.5 here. And they've got these, what are called gates, the red gate and the black gate that are crossing these. So the black gate they're using to show where the back wall is. That's what it's showing right here, 0.5. There's nothing currently crossing the red gate. But if we get over a spot where there's a flaw, and they've got a flaw about halfway down in this case, the sound is going to reflect off that flaw, and it's going to return to the transducer quicker or sooner than that sound that's traveling to the back wall. And so that's creating this spike right here that's at about 0.25. And they've got this red measurement gate. Now that you've got a spike that is going up towards that red measurement gate, that's what provides that measurement value up here at the top of the screen and kind of roughly just left to center. And we still have a back wall echo, but it's been reduced now over at the 0.5 area, because not all that sound is going to the back wall and returning. So our testers look a lot like this when we're doing it. They're a digital. Ours are actually touch screen, which is similar to this one. Older testers, oftentimes you looked at something more like this. And this just shows, they had screens that looked like this, and this is demonstrating what's called through transmission. And so here is where, remember, through transmission, we have a transmitter and a receiver. So in a good area or a non-cracked area, sound from the transmitter, ultrasound from the transmitter, is going to be able to fairly easily transmit through the part over to the receiver. And so what it's going to record is how long does it take to get from the transmitter on the left to the receiver on the right. Not only how long does it take, but it's going to record what the amplitude is, right? How strong of a signal are we receiving? So the time on the graph that shows up on our display, right below it, the time is given by the distance from the left side of the screen to wherever the receiving peak is. Okay, at the back wall. It just happens, it's at the back wall in this case. It's not called a back wall echo because we're not using an echo anymore. It's through transmission. It's a back wall transmission. And we would adjust our speed of sound and our scale down here in order to match whatever the known width this part is. When we're setting it up, we would set it up using a known test standard. And then as you can see, those two probes, the transmitter and the receiver, they have to be moved in parallel with one another. They have to be brought down together. And typically they're not linked in any way. So there is a certain amount of skill where you're holding probes on two sides of a part and you have to move them if you're doing it manually. There's automated systems that do this where the probes are always kept in alignment with one another. They use a CNC type process. But as this moves down, you can see what happens here is we don't get that middle pulse like we did with a pulse echo test, but rather our amplitude of our back wall through transmission, which on the left, where it was not blocked at all, it shows an amplitude of 9 on this 10-point scale. As we get to this flaw here on the right, a certain portion of the ultrasound is going to hit that flaw and it's going to bounce back to the transmitter. But the transmitter in this case, it's not going to do anything. Right? It's not going to pick it up or anything. The transmitter is only a transmitter. And so it will reduce the energy, or it will reduce the amount of that sound that is actually making it through the part to the receiver on the opposite side. And so the amplitude, the peak that it's picking up, that's being picked up by the receiver, is going to drop. So we've gone from 9 in the non-flawed area to it drops down to 5 here on the flawed area because it's blocking a portion of that sound. So we don't have a way, that's kind of the nice part. Pulse echo, we can actually we can create a measurement. We can say, okay, the flaw in this pulse echo part is at 0.25. With through transmission, we basically can say there's a flaw or there's not a flaw. But you can see this flaw that's in here. If it was closer to the transmitter or further away from the transmitter, it's really not going to change what this graph looks like below it. Right? It's whether it's blocking the sound or not. Now, what it will change is with pulse echo, as we move the probe, if this probe was further to the left, if just the edge of it was over the flaw, it would be bouncing back. What you'll get is when you first start to move the probe over the flaw, or before you get there, you won't have any peaks, right? You'll look like this. As you start to go over the flaw, you'll get something that it goes like this. And now we're at this point where it's centered, where the flaw peak is higher, the back wall peak is lower. And then if we were to continue to move the probe from left to right, now that flaw peak would start to drop and the back wall peak would start to come back up again. So we can kind of measure the width based on where those peaks start to move a little bit. That's different here is in through transmission, the narrower, if this crack that's shown here on the right were shorter, this back wall peak would be higher, right? Because less sound would be blocked. If we had a larger crack here, it would cause this peak to drop even further because it would block more of the sound to the point where if this crack that was in the simulated, in the cracked area, if it was wider than the face of the probe, your through transmission pulse here on the right side of the lower graph could potentially disappear altogether. You wouldn't have anything showing, okay? And then I also talked about angle beam, and I kind of drew this the other day, but here's a pictorial version of it, probably better than my drawing. And so a couple of things to point out. You can see the beam now. This is a known transmission, the red block here in front of the probe that holds it at an angle. One thing you got to be careful with is, so this is, in the top case, our sound waves coming out following this blue line. Right, there's our angle of refraction there given by, what is it, theta 2? And that sound wave is going to go in. It's going to hit anything that's in the weld. You can see as we move, if we move this probe left to right, they show going from the top to the middle here. As the probes move to the left, that sound, where that sound's hitting the weld, is going to move down. So we can actually scan up and down through the weld by moving that probe further away. The one thing you got to be careful of is if you move it too far away. This is on the primary sound path, or the first order sound path. As you can see, what will happen is as we start to move it even further away, now the sound is going to bounce off the back part, and then it's going to come over to the weld, and then if there was any kind of a flaw, it would come back. And so you got to understand that secondary, and this is where we get into the trigonometry aspect of this, is if you need to know how deep a void is, you need to know that angle of refraction, and you need to know the distance that the probe is from, and where you're going is the distance that the probe is at the point where sound enters the part. And so on your probe, on your angle probe, there's typically going to be like a line or some kind of a tick mark right here that shows you where the sound entry point is. And then you use a special calibration block to figure out that angle of refraction that's made of the same material that you're going to be testing. So if it's going to be steel plate, you have to have a steel steel standard test block. If you're going to be using an aluminum, you have to have an aluminum that's the same, not just steel or aluminum, but it has to be the same alloy and the same temperature as what you're working with. That becomes important as well. And so you get something that looks like this, and you can see this is much fuzzier. It's not nearly as clear as what we had before. And part of what's happening is when you're doing angle beam testing like this, here's our initial pulse on the left. You can see this is what kind of, if you look at the bottom, this green line that kind of has some waviness to it, that is the little bit of interference you get. And if you increase your gain, that'll become more prominent, right? That's just kind of the little bit of noise that ends up in the signal from sound bouncing around, maybe bouncing off of different atoms and that kind of thing. But here you can see as they move the angle or the probe, so you're really not getting much reflection here, right? If you have a good weld or a good bond, the sound's coming down, it's bouncing up, it's transmitting through that weld or that joint, and then it's continuing on its way, So we're not getting much of a response. But if it does hit something that causes an acoustic interface, a void, a crack, or something like that, then you get the sound coming down and bounces off that acoustic interface, returns to our probe. And so now that's where they get this. They're showing the peak right here. And again, to figure out how high or low that is, there's more involved than just pulling out a ruler. You're going to have to do some math to do the trigonometry when you know your angles. Other indications you might see is sometimes you'll get things like you'll get irregular indications. So you can see a back wall, often, the back wall indication we get, the initial pulse is very smooth, the back wall pulse is very smooth. Sometimes you'll get a flaw echo that's very rough like this. What would that imply? What may you have? This is typically what you see with corrosion. And so what's happening with corrosion isn't always perfectly symmetrical, right? If we have a part, and when we're finding corrosion, usually it's the backside. A common feature of finding this is, we looked at it with eddy current testing as well, is if we have, say, two pieces of aluminum that are riveted together, and we want to see if there's corrosion between the two of them without taking them apart. So if we have a piece of material and it has a corrosion area that looks like something like that, that's where you're getting the irregular back wall or the irregular echo like that. Is as our probe is sitting over it, a sound wave coming from kind of the middle of the probe on this example is going to have a fairly short trip. So that's going to cause the closest peak here, the one furthest to the left. And at another point, you're going to get some sound wave bouncing a little bit further, right? That's kind of the middle of that irregular. And at another point, you'll get some of the sound bouncing off a point that's further away. So that's where you're getting this irregular echo coming from, right? The other thing that's happening is the total energy is going to be fairly small, is often going to be smaller, because not only is sound bouncing up, but a sound wave hitting right here probably isn't going to go straight up. It's going to kick off at some kind of an angle, right? So that sound's not going to return to our transmitter, or our transducer. And so it's often a lower energy. You'll see this will be a much shorter pulse than you'll get if you have like a nice smooth crack or something like that. Some other things we have to be aware of is we have that initial pulse on the left side. And if we find a near surface flaw, it can easily be masked by it. What they show is a surface indication that is going to be covered up by the fact that this initial pulse is here. Now there's a couple things we can do. That's in that dead zone. That's that dead zone we talked about right in front of the face of the probe. There's a couple things we can do to try to avoid this or to try to fix this. One is if you turn the gain down, oftentimes when you get a big tail on your initial pulse like this, where it comes over to the right, if you bring your gain down, you can get rid of more of that tail. Okay. Now that will also decrease the sensitivity. So at the same time, this flaw indication will come down too, but you might be able to get it to a point where the tail drops off faster than the flaw indication drops off, and it would become visible. The other thing we can do is use a delay line probe. And so in my example here, that's essentially you take your probe, and that's where I was talking about you put a piece of known material in front of it, and then your probe is mounted above that. So now that initial pulse occurs inside of this, this known material that's part of the face of the probe. That's basically attached to the face of the probe. And so it moves the initial pulse away from the surface. Okay. So we're going to do this manually when we do it. To attach our probe to the surface, we're going to use a glycerin or glycerol-based gel. It's a clear gel. But there are other ways we can do it too. So another way we can do this is immersion testing. I mentioned this earlier. You can have a tub or a container that has either oil or water in it, and we can put our part in there and use that as our coupling agent. Okay, we can use the oil or the water as what couples the probe, and we don't actually have to physically touch the probe to the part when we're doing immersion testing. So that acts kind of like this delay line. Right? If we've got a part sitting in a tub and the probe isn't right on it, right, that you have what's called an initial pulse here. That's where the sound is coming out the face of the probe. You now have a front wall echo here, but it's usually very sharp and very defined. It's a very small one. It doesn't get that tail on the end like we saw here. And then the back wall echo that we would expect. And so that oftentimes can be used to find flaws that are closer to the surface that might get buried by the initial pulse if we were doing a contact method. So immersion testing is, advantages can detect those surface flaws. It can be done very quickly. This is often an automated process where the probes are moved. They're on like a 3-axis kind of, again, CNC, computer numeric control system. Most people are probably familiar with CNC like machining, where it's grinding parts. Well, works the same way. It's just not cutting material away anymore. So the probe is moved around the part, the object, and it can go pretty much any direction. And so it's very fast. It's automated, and then it uses that water or oil for a coupling. The downside is if you're using water, what's the downside to using water? What's water inherently cause problems with? Corrosion, right? They typically use pure water. They use like a DI water or something like that. so that it's less likely to cause corrosion, deionized water. It's the ions in the water that cause the corrosion issues. So if you have water where those have been removed, it's not as big of an issue. You just got to make sure you dry the part. But again, if you have a part that's got nooks, crannies, crevices, that kind of thing, there may be some challenges to making sure you fully dry it when you're done. So we get indications that look like this. Other versions of this are where the test specimen can be put in. The probe might be able to move a certain amount, and then whatever the test piece is might be able to move. It might be on like a table that can rotate, or some kind of a fixture that can move the part. So the probe stays more stationary, and then the part gets moved around as well. That's another option for that. So here, an example would be a probe mass that can go up and down, go left and right, can go front to back, and then the table here can rotate in order to kind of move it in any direction. So here's what one of these looks like set up. You can see it's fully computer controlled. This is a fan hub inside of here. This is where your fan blades would kick in. And so they can automate the process of looking for cracks in something like a fan hub. Okay. Or here's another version of one. So again, that's a fan disc, a fan hub. All the blades would key in there and would go into the tank. Here's your probe on a mast sticking out the top. You can go up and down, and then this fixture that it's on is able to rotate in order to perform inspections of all those different areas. So I've got a few videos that are interesting to watch. Jay, it's probably easier